Welcome to Part 6 of Applied Chemistry. In this section, we will explore the cracking of heavy residues, focusing on both thermal cracking and catalytic cracking. These processes are crucial in refining petroleum and producing valuable lighter hydrocarbons like gasoline and diesel. Cracking is a vital process in petroleum refining, used to convert large, heavy hydrocarbon molecules found in residues into smaller, lighter hydrocarbons. This is particularly important because crude oil contains a large portion of heavy fractions, but the market demand is much higher for lighter fractions like gasoline, diesel, and kerosene. Cracking helps maximize the production of these valuable fuels. Why is cracking necessary? Heavy crude oil fractions, such as fuel oil and other residues, are less economically valuable. However, lighter products like gasoline and diesel are in high demand, especially for transportation fuels. Cracking enables refineries to maximize the production of these lighter, more marketable products, improving both economic and practical outcomes. Thermal cracking is the simplest form of cracking, where heavy hydrocarbons are broken down by applying high temperatures and, in some cases, pressure. Thermal cracking involves high-temperature heating. Heavy fractions are heated to extremely high temperatures, between 450 and 750 degrees Celsius. Breaking carbon-carbon bonds. At these high temperatures, the bonds between carbon atoms in large hydrocarbon molecules break apart, creating smaller fragments. Formation of light hydrocarbons. The main products of thermal cracking include shorter-chain hydrocarbons, such as gasoline, diesel, and olefins like ethylene and propylene. By-product formation. Thermal cracking also generates gases like methane and ethane, along with coke, a solid byproduct. The mechanism of thermal cracking involves the homolytic cleavage of carbon-carbon bonds, creating free radicals. These radicals then react to form smaller hydrocarbon molecules. This process is typically random, resulting in a mixture of products. There are two main types of thermal cracking. Vis breaking, a mild form of cracking used to reduce the viscosity of heavy residues, producing fuel oil and small amounts of gasoline and diesel. Coking, a more extreme form of cracking that completely breaks down heavy residues into lighter products and solid coke. The two common methods are delayed coking and fluid coking. Catalytic cracking is a more advanced form of cracking that uses a catalyst to break down heavy hydrocarbons into lighter ones at lower temperatures and pressures compared to thermal cracking. This method is more efficient and produces higher quality products, particularly gasoline. Catalytic cracking involves feeding the heavy fractions. Heavy hydrocarbons like vacuum gas oil are introduced into a catalytic cracker. Use of catalyst. A catalyst, often a solid material like zeolite, lowers the activation energy, allowing the reactions to occur at lower temperatures, 450 to 500 degrees Celsius, compared to thermal cracking. Cracking reactions. The catalyst helps break carbon-carbon bonds, creating smaller hydrocarbon molecules such as gasoline, diesel, and olefins. Catalyst regeneration. The catalyst gets coated with coke during the process, so it is sent to a regenerator where the coke is burned off, allowing the catalyst to be reused. Catalytic cracking involves the formation of carbonium ions. The process begins with protonation, followed by the creation of carbonium ions that undergo rearrangement and breakdown, forming smaller hydrocarbons. The catalyst controls the reactions, ensuring higher selectivity for valuable products like gasoline. There are two primary types of catalytic cracking. Fluid catalytic cracking, FCC, this is the most widely used process. The catalyst is a fine powder that behaves like a fluid when mixed with vaporized hydrocarbons. Hydrocracking. This process involves the addition of hydrogen gas, producing more saturated hydrocarbons, resulting in a higher yield of high-quality products like diesel and kerosene. Let's compare thermal cracking and catalytic cracking. Temperature. Thermal cracking occurs at 450 to 750 degrees Celsius, while catalytic cracking operates at lower temperatures, between 450 and 500 degrees Celsius. Pressure. Thermal cracking often requires higher pressure, while catalytic cracking operates under moderate pressure. Catalyst. Thermal cracking does not use a catalyst, while catalytic cracking employs zeolites. Product selectivity. Thermal cracking produces a random mixture of products, while catalytic cracking is more selective, primarily producing gasoline and diesel. Coke formation. Thermal cracking generates a significant amount of coke, whereas catalytic cracking results in lower coke production. Energy efficiency. Catalytic cracking is more energy efficient, as it occurs at lower temperatures. Product quality. Catalytic cracking yields higher quality fuels, especially gasoline. Cracking plays a crucial role in the petroleum industry. Maximizing fuel production. It converts heavy hydrocarbons into lighter, more valuable products like gasoline and diesel. Improving refinery economics. Without cracking, a large portion of crude oil would remain as heavy residues with lower market value. Feedstock for petrochemicals. Cracking produces essential feedstocks like olefins, used in the production of plastics, synthetic rubber, and other materials. In summary, thermal cracking breaks down large hydrocarbons at high temperatures, resulting in lighter hydrocarbons and coke. It is energy-intensive, but effective. Catalytic cracking uses a catalyst to achieve the same result at lower temperatures, yielding higher quality products, particularly gasoline, with less coke formation. Both processes are vital for converting heavy fractions into lighter, more valuable fuels and meeting global energy demands while optimizing refinery operations. We've reached the end of our detailed exploration and covered different topics in this video. Thank you for watching, and don't forget to like and subscribe for more tutorials on applied chemistry and other exciting topics.